Hello and welcome to Science on the Edge. Today I'm lucky enough to have Professor Lee Cronin with me to talk about abiogenesis amongst other things. It's a very fascinating topic. It basically means the origin of life. We're still trying to work out how life originated on this planet, and Lee Cronin is definitely someone that knows a little bit about that. He's actually tried to create his own life, in fact, on this planet in a sort of way, and we'll definitely be covering that topic as we move along. So without further ado, Professor Cronin, could you give my audience a little bit of an overview about yourself and your areas of research?
Yeah, so I guess I'm paid as a chemist at the University of Glasgow, and I've been there for a few years, about 18 years. Before then, I was in Birmingham, and then in Germany and in Edinburgh doing postdocs. Although I'm a chemist, I really see myself as a kind of almost a natural philosopher of chemistry, and that I'm interested in why I suppose life manifests at the chemical level. And I guess from background, my hobbies from when I was younger was I used to do a lot of computing. I used to design and build my own computers since I was, I don't know, maybe 8 years old. And I obviously became a chemist, and I've been trying to fuse computing science and chemistry together ever since I suppose I was 8. And so there's a whole bunch of new theories that we've been developing and new ideas. But really, through the medium of chemistry, I'm just interested in understanding how information processing occurs in the universe. And we know how that occurs through biology as a starting point, and ask questions like, is biology the only way that information emerges in the universe?
Okay, so so your background is I know you said chemistry, but it's almost bioinformatics in a way. The combination of chemistry together with computing. Would you agree with that, or is that a bit of a stretch?
No, I mean, I suppose I'm a fundamental. I'm really interested in pure mathematics and fundamental mathematics. Always have been. And I've always found it easy, but didn't really realise I found it easy because I was actually in the learning difficulties classes at school, and that I wasn't allowed to do math. I wasn't taught maths, so I had to teach myself maths. And so I'm interested in abstraction. And then I'm interested in chemical informatics, I suppose, from that now. And I guess that's strictly analogous to bioinformatics, except chemical informatics is a bit harder than bioinformatics because you're talking about three-dimensional space.
Okay.
And dreaming up, graphs or drawing. What I mean by a graph, I mean a finite graph, which is a drawing of a molecular representation of a molecule, how you draw that and explore it in computer memory. And I'm really interested in how mathematics is manifested in chemical systems.
Okay.
Did chemistry invent mathematics?
Do you know much about Max Tegmark?
Yes, I know Max.
You know Max. So because he seems to have a similar sort of attitude to the universe. I mean, there was a book that he wrote not long ago. It wasn't Life 3.0. It was before that, where he basically seemed to be implying that the universe is mathematics. That's what it is fundamentally, and everything else is just a way of interpreting the mathematics. Do you agree with that idea?
No.
No.
So Max argue about this. We have argued when we met once or twice about it. No, what I see is that the universe is this natural thing, and life emerged in the universe, and life is able to generate abstraction. I'm able to generate, and I invent mathematics.
Okay.
That doesn't mean mathematics is the universe is mathematics. The universe is something else. It's really interesting, which is consistent with mathematics, but that's like many hours of podcast. So I would say that just because we can invent mathematics doesn't mean the universe is mathematics. That adds the wrong symmetry. And also Stephen Wolfram, who keeps inventing new types of way of looking at the universe through his lens, is kind of deluded by this as well, because we can't capture yet all the richness of the universe in all the mathematics. That doesn't mean that we won't be able to. And I'm an absolute materialist. There is nothing other than the universe. But
so you're not a Kantian. You don't think there's some metaphysical universe out there that we could never ever perceive, because everything we do perceive has to go via our senses.
We create it. Yeah, we create the Kantian universe in our brains.
Right.
And and we can I guess we can share common Kantian universes that are but they actually are in the cells in my brain, so they do exist.
Okay, okay.
And so I'm really a real practical materialist.
So Hume, basically. Hume is where you're at.
Kind of, yeah.
Yeah, well, me too, to be honest, me too. Okay, so could you, actually, I'm just thinking now, you're talking about the sort of work that you do. The work you're doing now would have probably been impossible if you'd have reached maturity back in, say, the 80s, wouldn't it? I would assume, based on the fact that we didn't have the computing technology and the bioinformatics that we have now. Would you agree with that?
Well, so I suppose I don't know what I would have been if I'd gone to university earlier. I probably would have gone to university because it wouldn't have been allowed. I mean, I really had to fight very hard to get out of the kind of the school system into university.
I got in through clearing myself.
Yeah. So I mean, it is tough, but I think that actually I invented a lot of the techniques that people are using today many years ago, machine learning and using evolutionary algorithms. And I think they're being popularized now. But I think what's helped me dramatically is the advent of the cheap microprocessor and cheap computing technologies that you can just bolt together. But we'd always been slightly before that in our own research. Right. It's just got cheaper and cheaper and cheaper. And we are just customizing and customizing as we go at the moment. And what we're trying to do is actually develop new standards, because the problem with all this cheap computing technology is that people just can hack together any old thing, but you don't have any common device, you don't have a common language, you don't have the right ontology. And what I mean is the right abstraction level to make sure that a robot I build in my garage can be programmed in the same way a robot you build in your garage. And I think what we're trying to do with chemistry, by the digitization of chemistry, which I can talk about with the Abiogenesis machine, is to make sure that all the labs in the world can have an internet of chemistry to basically have a massive biogenesis engine, which spans the planet.
So you want to avoid the replication error that the psychologists have got, basically, by making sure that you all do everything the same, so to speak, or at least using the same tools.
I think that's, well, I mean, the psychologists have a problem in that their replication problem isn't because of, it's because they don't actually have it is very similar, right? And that psychologists don't know what to control for, right? And they don't know what they're looking at. And so they're getting better at it, of course. And human brains and human behaviors are really complicated. So I'm not saying it's because they're poor experimentalists. What they're doing is multidimensionally hard. Yeah. Chemistry is still quite hard. Everyone at school hates chemistry or remembering the facts, but basically...
I just hated the molarity calculations. That's the bit I hated.
Easy, just Avogadro gets you there. And I think that, or reading actual good old history of science and looking at what Dalton did, because Dalton was a meteorologist and he became a chemist and he worked out all the molar ratios. Yeah. I think that the key thing is that chemistry needs to be controlled, and chemistry is intermediate, I suppose, in between physics and computing science. Computing science, you run programs, they have to work. You know, if you give code to someone, they have to run it on their computer, or otherwise, you're not going to buy it. So, and I think that that's a really important problem that chemists have yet to solve, and that's, I think. By having an architecture that's uniform, makes it programmable. So that will not just remove the reproducibility crisis, but you need a new language to express that chemistry, so that it can be basically, you know which test tube to use and what liquids and what chemicals and what orders were at them. But actually, it's not hard. It's the same as, writing software using the advanced programming languages we have now, because everything's in a library anyway, right? People don't actually write code anymore. They just write linkages between code.
Yeah, that is true. I worked in computer science for a while before moving into biology, and when I first started, yes, I was writing code. I mean, like yourself, as a child, I had don't know if you remember these. I had a Commodore 16. And I remember writing programs in BASIC. That was the first language that I used. And as I progressed, you needed to know less and less about coding. You could just download entire libraries, get something to happen without having a clue really how it worked, which I suppose takes you away from the core of it.
Well, the computer I built used a very simple processor, and I actually had to program it using kind of almost a kind of assembly language, right?
Wow, wow.
Or I was really bashing bits into a processor and had to actually understand the logic array that gave me, the words I needed to put into the shift registers. I had to build the shift registers, if you like, or at least the kind of build a way of accessing those shift registers. And then my first real computer, after I broke my mother's washing machine, TV, telephone, to build my first computer, I took the processor out of the washing machine. I used the telephone to kind of program it, and use the TV to display an output, even though I didn't have the right kind of interface to even get to control a CRT, which is what you had to do, right? Because you had to have a digital to analog circuit. But anyway, I then had the ZX81.
I'm just not understanding how you were in a remedial group for education, considering what you've just told me that you did yourself at home.
Well, I mean, I've always been interested in why everything worked. And I guess the problem I had at school was I was not very communicative. I wasn't able to stick with the syllabus, and they didn't think I was making progress. Okay. And I was always telling them I knew the answer, but and then doing other stuff. And I think, to be fair to them, probably the educational system at the time, you can't cope with that. Is, if someone isn't progressing and doesn't appear to understand or able to make progress in the class, then they get demoted and to get more help. I was just bored. I was absolutely bored, stupid, and I was busy doing other things. I spent most of my time in the chemist, buying chemicals to just set fire to, or in the library getting books to try and work out how to build stuff.
I spent my childhood reading science fiction and biology. I read The Selfish Gene, I think, when I was 11. Okay. So I spent a lot of time in the library and reading things that had nothing to do with what I was being taught. So it sounds like a similar kind of background, really. Okay, so let's talk a little bit about abiogenesis, because I think this is a topic my audience will be fascinated with. Could you explain perhaps what abiogenesis is and what your role is in trying to unravel that term?
Yeah, so I think that what it is it refers to a sequence of events that would turn what would be, say, an inorganic or a dead planet, a planet that was pre-life, into a living planet. And so that the genesis process of producing biology obviously was abiotics. The term abiogenesis refers to the fact that you start with a non-living planet, there is a process, and then, hey, presto, you have a living planet. Now, there's lots of people who speculate about how that might have happened, which we can go into in a moment. But to keep it well structured, really, for me, abiogenesis is just like saying, when did I start with a dead planet, right? And the dead planet was and then at what point in time is that planet ostensibly alive, like it looks like now? Because I think the problem we have with life isn't an on-off switch, and evolution isn't an on-off process. And I think I'm beginning to realize that abiogenesis wasn't just one event, it was many, many events coupled together. And in fact, the universe, there are hidden laws in the universe which make abiogenesis work. I'm not saying there's something, again, going Kantian. I'm just saying there's missing understanding of how physics and chemistry work together to give us abiogenesis. So what do I mean? Well, Earth before biology was just chemistry, rocks, fairly boring. Abiogenesis, then there is chemistry on Earth in biology, but there is a memory. And so I would say that if biology is simply chemistry with a memory, abiogenesis was the process of generating a way of recording information from the environment to enable the object that was looking in the environment to survive.
So are you basically saying that life basically is inanimate matter with memory, and it's that memory that makes it life? Is that your definition?
And so I would say the purpose, yeah, so I would go for, well, not yes and no. I would say that the purpose, the process of acquisition of memory gives inanimate matter, it animates inanimate matter.
Okay, okay.
And so that is really interesting, because obviously the rocks in your backyard aren't crawling up and down the hill unless there's a
Hmm.
something happened. You know, there's some soil erosion or there's a
I
waterfall.
suppose a flame can crawl up and down a hill, though, and it can replicate, but it doesn't fit the definition of life because it has no
No,
memory.
a flame has no memory. A
Mm.
flame has some dynamics which you can write down, but a flame has no memory. So I would say, when I talk about memory, I talk really, and what we can say now is biology on Earth right now has an open-ended memory, in essence, an infinite RAM, whereas the flame, when this is why we always get fooled, only has, like, 1K.
Okay, okay.
Like your Commodore.
Like my old Commodore 16, yes.
Yeah,
16K.
So the fact is that the flame does have some things it has to maintain, but the path from the laws of physics to that combustion dynamic is very small, and so the route to get there can happen very quickly and uniformly. And if that's the case, then there's no heterogeneity.
Okay.
And if there's no heterogeneity, then really all the flames are basically the same, and there's no need for evolution. There's no real competition. A flame is a flame is a flame.
So it's about if something can maintain memory for long enough, and then pass that memory to, well, I don't want to say a child, but a descendant.
No, a child is fine. A child object.
Child object. Then you have life, basically.
Yeah, and
Okay.
I think that's all life is, really. Life is the process of acquiring knowledge from the environment inside an object. So abiogenesis, so life, I mean, look, life doesn't really exist. If you really want to blow the minds of the people looking and listening to the podcast, life doesn't actually exist. Life is not really an on-off thing in the same way the universe exists. That makes sound I'm being really, scandalous, like Brexit, no Brexit in between. I'm saying that what life tends to be is, like, there's nothing special about the matter in my body, but there is something special about the organization of the matter in my body. And that organization has been, if you like, recorded over 4 billion years.
So would you say that life then is an emergent phenomenon, a sort of meta-phenomenon on top of matter?
You could call it that. I think life is the result of selection. And the missing force in the universe that we need to find is the force of selection. And so selection...
Is that not just time?
Sorry?
Is that not just time? Because obviously the
No,
more time...
because you can have selection in the, you can have non-selection. So you need something very special for selection. So so again, selection doesn't give you. So if you look at, say, the universe with stars and galaxies, and everyone will say, oh, well, they're alive then with selection. No, the effective memory of a star or a galaxy, again, is a small number of bits, because the number of dynamical components. So what selection gives you is the ability to acquire those memories over time, and that selection is over time evolution. But open-ended evolution can only occur really efficiently in biology because you have a number of things. You have a cell. That means you have an object where there's an inside and an outside, and you need a self in a population for really efficient selection. I mean, you can see that, be it COVID-19 or bacterial viruses, or just basically looking at how animals on Earth have evolved. So I think that selection is that force in the universe that only emerges when you have the ability to make a long memory. Now this seems very esoteric, but it's actually quite profound.
What is your definition of long, by the way, in this term? I mean, is there
a
minimum point?
So I say, well, actually, sorry, yeah, you're right to pull me up on that. So I mean, a long memory, that is a memory that persists for some time, a long time, millions of years, well, let's say years, well, let's say months and years, millions of years. Then that's one dimension. The other dimension is number of bits. So if I give you a secret message, I don't know, I remember a poem and I give you that poem, that poem isn't just going to randomly remake itself, right? I have given you some privileged information that you're storing in your brain. Same with the biology. Now, the universe doesn't in general do this unless you have chemistry, and chemistry can do very interesting things. It can form bonds. And at the back of my office here, I actually got some examples of a molecule. So here's a molecule here. This is just a cluster. And this cluster here has atoms in it. This is the metal atoms, blue atoms, and you can see the oxygen atoms in red. And they're connected together by bonds. And you can see this cluster looks like a rugby ball. And there's a nice atom in the center here, an iodine atom. So without those bonds, that molecule would not be held together. So my first interesting thing I'm going to say, which you might not hear anywhere at the moment, is that for life you need bonds, or the most primitive life that emerges in the universe, because bonds allow you to basically connect atoms together in a particular configuration, and that is the start of your memory.
Okay.
And so you can then you can imagine getting to DNA, RNA, and then proteins and so on. But where there's a bond, there's a potential memory. But in a flame or in a star, or all the bonds are burnt, they're broken, they're too high energy. So the atoms can't have any registry, your message is lost.
Okay, that makes sense. That makes sense. So going back to abiogenesis itself on this planet, how do you think life arose on this planet? When I was a child, I was just taught there was a primordial pond somewhere bubbling away, and the right chemicals came together. There was a bolt of lightning, and suddenly you had a replicating primitive cell. Obviously, in more recent years, we've started to hear that life is more likely to have arose next to some kind of volcanic vent in the deep sea, because the surface of the planet was just not safe for any kind of life. Where do you believe that life arose? And could you explain to my followers what form that life might have taken?
Yeah, okay. I think so. I'll give you the very honest answer that I have absolutely no idea.
I suppose no one can really.
But but I know the experiment to do, which is kind of interesting. So that's, and I think that the other problem that comes with when people thinking about, what is your version of how life began, is everyone has a version. And the problem is there is no real test. So one of the things that I thought, well, I'm going to make it, so the only belief I have, and it's a belief based upon some intuition I developed as a chemist. I used to love setting fire to things, blowing things up, like the kinetics of chemistry. And chemistry happens really quickly, right? Chemistry doesn't take trillions of years. It takes minutes, seconds, milliseconds, not months. So I thought, so one of the things I'm playing with is, couldn't it be that life or selection was able to act relatively quickly? And then we actually went from in the same way that water turns to ice when you get to the right temperature, chemistry turns to biology like that, like in hours. Now,
in hours?
In hours. Now, that doesn't mean you make a fully fledged ribosome, which in the ribosome is a very complicated machinery you have in a cell. But let's just think that maybe in just a few hours under the right conditions, chemistry can compete with different bonds being made and broken, and some molecules are smarter than other molecules, can store more information. And then when those molecules are stored inside an oil droplet or some kind of container, that container becomes as smart as the molecules they've just included. And there's a dumb oil droplet over there.
Right.
And it's the name of the game is for the oil droplet to survive, persist, and copy. It needs the smartest molecule to acquire resources, copy itself. So it basically is like copying everything, right? Something like this. So I can tell you about what the process feels like, but I have no idea. I don't care about what the molecules are, right? And I think that it's really the wrong way to look at it, because we're being basically dissecting and going backwards for 70 years at least, and we actually haven't got anywhere. Now, the prebiotic chemists who working in that area might be offended by that and say, well, we have got somewhere we can make RNA, we can make this, that, and the other, but we have to put in information.
But RNA seems to be the favorite at the moment, doesn't it? It seems that more because it can be structural, like a protein. It can carry information, like DNA.
The problem with the hypothesis in isolation, I don't think it. It doesn't have to be in isolation. Is that the RNA molecule is too complicated to have arisen by chance. So that means there needed to be a very primitive living process that made RNA. And what I think we're going to find is there are many versions of life going all the way down. And that there was a big bang, if you like, first primitive life form able to store memory. And then the amount of memory and the longevity of the memory increased. And then it probably got stuck. And then it generated more machinery. And then at some point, we got biology as we know invented. But there were lots of competing biologies. There wasn't one route. Lots of different routes.
Did you think life then could have arisen more than once independently on this planet?
Had to. Yeah.
Really? So there wasn't one root at the tree of life that everything now is descended from?
No. And I think that's
because that's a consensus generally, isn't it?
That's such an obvious thing to try and go for, because anyone who can see where that root is broken will show a very, very, very important light on how biology is on Earth. Now, what am I saying? Am I saying that all life on Earth right now isn't descended from one root? No, I'm not saying that isn't the case. It looks to be the case. But we just frankly don't know if there aren't other life forms there. Now, the question is the current form of life we've got on Earth, and that descended to Luca, the last universal common ancestor, did Luca have the special mixture of RNA, DNA, metabolism that we all need, the lipids, the fats, and so on, and that there were no other versions? Or were there many Lucas, if you like, and many life forms, and that just there was one life form, so you went, you know what? So here's my conjecture. There were many Lucas, many types of life. They all used roughly the same chemicals, because there was this initial selection, initial biology, where the biology was happening, but slowly. Then biology got going, and there was I'll use these amino acids in my kingdom. I'll use these amino acids in my kingdom, and then carry on. And it wasn't very efficient. And then what happened is that when evolution started to kick in a finite way, it needed more resource. And that resource limitation needed to then gather stuff, and there was an arms race, a war between the different Lucas. And one Luca won, and that's it. The winner is here. And all the memory of all the rest is gone.
could it have won, though? Or perhaps it was like the origin of eukaryotic cells by the endosymbiosis. Could it not have been that one absorbed the other, it became part of it?
So. I think there's all sorts of fascinating questions there. That it didn't have to be a war. There could be some arguments and some, way that things go together. And I just think we just don't know. Right now, we look at what we see on Earth, and we are able to say, isn't it profound that all life on Earth seems to be connected? That's a wonderful thing. It seems to be a current fact. But that doesn't mean that all life on Earth was all connected to the same roots when it came with genetics. We're obviously all connected to the same chemistry.
Yeah.
So I think there's lots of interesting questions. I would love to go deep in the Earth, go to Lake Vostok, go all these places. It would be great to be able to go somewhere and find examples of pre-Luca life that had slightly different chemistries. And there's no reason why they don't exist. It's just that probably when life took over on Earth, to be successful, it had to become a planetary phase transition.
Okay.
And there are good theoretical physicists out there. There's a person in ASU, Arizona State University, Sarah Walker, who one of her main conjectures is that life was a planetary phenomena. And I'm kind of saying, well, as a chemist, I think it's a beaker phenomena, but maybe biology, when it got established at Luca level, was a planet. The planet had to basically decide on one common genetic code, if you like.
Okay, so do you believe that perhaps on other planets, if life originated there, it might be a completely different Luca and evolved down a completely different route with different structures?
Yeah. So I have, is it belief? I don't like the word belief, but
belief is a wrong word. I don't like it either, actually.
But I think my intuition, based upon my bias, there you go. That's almost a belief, right?
Good scientist.
Is that there is, we might find Earth-like life around Earth, and it'd be interesting to see how far does it go. Mars, maybe, no further. But there is life elsewhere in the universe, or there is the process of the universe learning to remember stuff through chemistry all over the universe. And there's no commonality. There's going to be, that's an absolutely ludicrous statement to make.
Well, I suppose the universe has been around for 13.9 billion years, and there's 100 billion stars in our galaxy, billions of galaxies. it's highly probable, well, in my opinion, not belief, that it probably does exist somewhere else too. But what about intelligent life like ourselves? I mean, we haven't seen any evidence of it yet, and we've been looking for quite some time.
Well, well, just because that's probably that's no proof that there isn't intelligent life. But I would say on Earth, intelligent life took a long time, and that's why maybe I think intelligence might be more common than might be quicker than life on Earth. Now, what I mean? Well, the reason why intelligence on Earth took such a long time is because I was thinking about this the other day. It's kind of interesting. Is because of the gravitational strength, the size, the mass of Earth, and so on. Now, let's think about it. So, what happened is that for us to move around on Earth, we needed access to certain energy molecules, and until we had invented, basically started to have mitochondria in our cells.
Which took a long time.
Yeah, it took a long time for that to occur, and we weren't really able to break that energetic bottleneck. And so we didn't invent intelligence that quick. So I'm wondering, I was fantasizing the other day that maybe on other planets where the gravitational force is lower, we've got chemistry going on, and the energetic requirements for moving around and stuff were lower, maybe you get to intelligence faster.
But of course, if you've got a lower gravitational pull, maybe your atmosphere would leak away like it did with Mars, and life wouldn't have as long to develop.
So I don't think that. No, I think Titan has a good amount of has one atmosphere. So does Venus. The reason why Mars apparently is suggested to have lost its atmosphere, it's not entirely clear, and I'm not an expert. So everything I tell you now is remembered and probably made up because it sounds. But I think because Mars doesn't have plate tectonics and it doesn't have a magnetic field.
Okay.
The idea is that it was that the solar wind basically just blew it all away.
Right.
And yes, its mass plays a role, but there are other ways you can compensate for that. So I think Mars, for that size, at that distance to the sun, yeah, game over.
Okay.
Because basically nuclear, the nuclear processes that were driving the core could not be sustained. Surface area to volume ratio, that there was not enough volume in Mars to keep a mantle, a molten core mantle and a magnetic field for very long. As soon as that went, boom, your atmosphere goes. Where Earth, it's a bit larger, okay. But again, I think I just made that up, but I think there is some, that the planetary scientists might kind of back some of that up, but I'm not qualified.
That makes sense. Plus, I suppose some of the moons around Jupiter, for example, Europa, they're being pulled and squeezed by the gravity of Jupiter and other moons, and that creates heat in the core.
Yeah. So I think looking for life on the out, but I think looking for life in our solar system further out is really interesting. But I think the problem is a bit cold. But I think there's one candidate where there is probably life, or at least there is selection going on right now. We should go quick.
Europa.
No.
Titan.
No. Well, we are. Yeah. So I think we should go to Europa and Titan, but even cheaper, even quicker. I think we should go to Venus.
Venus, really, with overheating the pressure.
If I'm right about how biogenesis works, then Venus is alive, or at least Venus is in the process of creating inorganic memories.
Okay, so where would that life be? Would it be in the clouds? Would it be on the surface? Would it?
Yeah, I think it'd be everywhere. I think there's going to be life in the clouds, on the surface. Venus might be a very good candidate where you've got lots of different. It's pre-Luca, pre the final thing, and then there's different life forms in the clouds and life forms on the surface because of the massive difference in pressure and temperature.
Okay. I mean, how could we test for that? How could we? I mean, what would we see evidence in the clouds? Would we see some discoloration? I'm trying to convince
someone to fund a private mission to Venus, and we're going to dump a mass spectrometer and a microscope down through the clouds. It wouldn't cost that much. Basically, a couple $100 million tops.
Wow. Well, so there wasn't a mass spectrometer in. Was it Magellan that landed? No, it wasn't Magellan. The probe the Russians sent to Venus that landed, did that not have any kind of?
I think detectors? So. There was some very rudimentary devices on that, but it was many years ago. But I mean, it's fascinating. The Russians went to Venus and they got some really interesting data, and no one's been back. And I just don't understand why. It's like the problem with launching, going to the outer solar system like Europa and Titan and Enceladus. all these water worlds that people want to go to, is you need so much fuel to get there. Going to Saturn and Jupiter is hard, right? I mean, you know, I think that I can't remember which one is furthest out. Let's get it the wrong way around. But basically,
Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto.
So
oh,
Saturn
no Pluto anymore.
So Saturn is quite a substantial distance further. I think Saturn is 83 light minutes from Earth.
Yeah.
That's far away. So if you want to get a probe to Saturn, you need a big rocket, and you've got to getting into orbit on the moon around Saturn is really hard. I mean, you're talking about a $6 billion mission, right?
Whereas Venus is easier.
And to go and look for life in something that's extremely cold and it's got water on it, and we say, well, there's water on Earth, therefore, and there's life on Earth, let's go to somewhere really cold where there's water because there'll be life there. And I'm like, as a chemist, well, yeah, okay, I would love to go there too. Don't count me off the mission of, you know, getting some data. But I think there's a much cheaper candidate, and with the current spectroscopy and tools, going to Venus is something we should do as soon as possible. We could do it next year, you know. Elon Musk could lend us a rocket. We could basically make a probe, bung a few mass specs on, a few mobile phones, a few parachutes, bung it down through the atmosphere. Okay, they'll get crushed, but we get some really interesting information. But you know, that's just a little dream of mine.
Maybe the next time you meet up with Mike's Tegmark, you can ask him to pass your message on to Elon. I've heard they're quite close.
Yeah, so I don't think Elon's interested, but I am talking to a organization that's very well funded, where we are seriously considering missions to the inner and outer solar system. And you know, I can't say very much more because I want to see if they're going to pay.
Wow, that's fascinating. That's fascinating. Okay, so winding back slightly, could you tell me a little bit about your work, your own work, in this field? For example, the little box behind you with the flashing lights, I believe has something to do with your work.
So that is a little a cube. It's actually playing a game of life, Conway's Game of Life at the moment. So in my lab, I guess we're principally trying to answer, I guess, 4 things. We're trying to make an artificial life form, and I'm not really big on the origin of life. I originally called the group The Origin of Life, but I've never really intended to research the origin of life because there's too much dogma, there's too many arguments, there's too much emotional baggage that gets in the way of actually coming up with good conjecture. So look, let's just make an artificial life form. How hard can it be? My group like, okay. So that's the project. That's the big team making artificial life. Then I thought, well, if we're going to make artificial life, we need those Genesis engines that we can talk about in a moment. We need to build some robotics. And that robotics, I then got me to the next big thing we're doing in our group, which is the digitization of chemistry, which is using robots to make drugs, to make molecules, to do discovery. So we've got a load of robots in the lab that do drug discovery and make molecules on demand. In fact, you can now program a robot using our chemical programming language to make any molecule. And that's really exciting. And then I thought, well, if I can use robots if I can program a robot to do chemistry, can I use chemistry to program a robot or to be a computer? So that's the chemical computer part. And in my lab, we're making chemical computers that play games of life like this cube that's here at the moment, for all sorts of things. And then the final project, which is this more philosophical overarching thing, is to say, what is it about chemistry that allows the universe to make the transition to information? Now, this is a kind of heretical statement if you're a physicist, because physicists have God complexes. And physicists, when you say, is there information in the universe? They'll say, oh yes, look, there's information everywhere, the stars, the planets, blah, blah, blah. And I'll say, well, that's not information, that's data. So yes, the universes are composed of many particles, those particles in many different positions that constitutes information. But universes that are alive have information, because information represents encoded and decoded knowledge. So universes that are dead do not have information. So the universes that invent life become informational, because I'm now able to, let's say I can go and build something in my workshop. At the moment, next week's plan is to build a cloud chamber, because I want to basically make a random number generator with charged particles, just for fun. So I'm going to build that. I'm going to do it. Maybe I'll write down how to do it. And there's plenty of DIYs online. But I can say, Mark, here you go. Here's my hobby. Here's all the information to make your own cloud chamber. Now, giving you that information, you could go and then buy the same materials I bought and you could build it. That information has meant something to you, but as an encoding and decoding process. Let's go all the way back to biology. So in my cell now, let's say my cell decides to open up a bit of my genome, one of my chromosomes, basically takes that piece of DNA, that DNA then gets transcribed into RNA, my ribosome or machinery then uses that RNA and its transcription process to then produce proteins. And that's almost genetic information is used to make a protein. That protein has a role. And so, although biology is not writing, music or books or telling me secrets that I can tell you, at one level it is also processing information. So what I mean, and it all goes back to this concept of memory. So I define information as being something that can be encoded, decoded by a living system. So I'll say that again. For me, there is a certain type of information that is all information actually, but information can be only made and read by living systems. All the other stuff is just data. So that's the big philosophical part of my group. So my group has, and as you can see, I'm even struggling to tell you what I mean, right? So
information. Just let's see if I get this straight. So data is just all the random numbers, sizes, weights, positions of objects in the universe. Information is the ability to organize that into some sort of pattern and then to pass that pattern to some other life form so that they can see the same pattern that you saw. Is that it? Yeah.
And so living universes have information in them, dead ones don't.
Okay. I mean, I suppose dead things, though, can keep a sort of record, but they can't pass it on to other systems.
They don't keep a record, do they? Because there's no observer to say there's a record.
That's a good point, actually. No subjective experience.
And I think that what we might understand and what work out in the end is not just this universe, but all universes in the end have to be alive. In that if selection, I think the selection is as fundamental as gravity.
Okay.
And the same way that gravity emerged in the early universe, right? Or electromagnetism, all these different forces, they all emerged after the creation. Well, let's not say the creation, the cooling of the process, right, through the cycle. Information did the same thing. And maybe that's it. Maybe that makes you feel a lot more comfortable that biology is a natural consequence of the universe doing its thing. In the same way that, pulsars and neutron stars and black holes are a consequence of the universe that's doing its thing.
Have you come across David Chalmers at all?
Yeah.
And in his idea that everything in the universe is conscious to one extent or another, even something as little as an atom has the vaguest primitive version of consciousness.
It's just nonsense.
It's nonsense. You don't buy that.
Well, it's like, it's like, actually, David says something much more sophisticated than that. But
I was simplifying it.
No, you're not talking nonsense. I hear people said that before. So you haven't misquoted. It's like people take that interpretation. There's also a guy, I think, a really interesting philosopher called Philip Goff.
Rings a bell.
Yeah, who also talks about consciousness in the continuum. So what I'm now going to say is, that was nonsense. I'm going to say, right now, why is it nonsense? So I would say that when particles interact with one another, they do at one level in experience a cause and effect. Now,
so they pass on information.
Not yet, because there's no memory.
Okay.
And so what I'm trying to say, so I haven't met David Chalmers, and I would love to discuss this with him because I think he's done some super, really impressive work in this area. That basically, I know what he means, but he's not there yet. He's on the same trail that I'm on for selection. So I think that basically consciousness is consciousness is actually selection. And only when you have a large enough memory does this thing called consciousness or this informational thing actually have any context. You could say the electron in an atom has a degree of consciousness, and you could take my consciousness and divide it by the number of electrons in my brain, but that doesn't really help you. right? And so there is an emergent process. Now, what I think Chalmers is trying to say is that anything can be conscious if you are able to organize the structure correctly or allow that structure to emerge. Totally agree with that. And are trees conscious? On one level, of course. Are all living things conscious? Is a bacterium conscious? Yes, it may not be dreaming about TikTok or whether Donald Trump is going to win the next election, or whether, I say me worrying about my next paper to be kind of accepted or convince the editor. But there is some awareness of the surroundings.
Right.
And what the bacterium is able to do, some very primitive level, is it's aware of the surroundings. So it can then, let's say, think, but not think, maybe compute or be prepared for what might happen next, to therefore adjust its state accordingly. So that's a continuum of consciousness all the way down to just response to stimuli.
So it's a dimmer switch, basically, rather than an on-off switch consciousness. Yeah. It can be all the way down, all the way up, anywhere in between.
And I mean, I think strictly consciousness doesn't exist because I can't measure it. I know that when I was given CERN, at TEDx CERN, a philosopher and I had a big argument about this. I think it was John Searle, actually, but it doesn't matter who it was. But the thing called, I think consciousness is something.
But I think, therefore I am Descartes. Surely that's proof.
Yeah, maybe. But then some undergraduates, when they've been, in your lectures, you wonder if they are conscious. But I'm saying I'm doubting that you are a person. I'm just, the term consciousness for me is not measurable.
Okay.
And so right now, if I can't measure it and there's no theory governing it, I'm kind of a bit phased, a bit like, the way selection works. Right now I'm working on a theory of selection and complexity that becomes measurable. And once I've established that, I can then use that tool to tell me something about how the universe works. It's a bit like, looking at, say, gravity. And until I was able to measure the effects of gravity, I knew that stuff happened, but I didn't really quite know how to quantify it. So I think that right now, for me, conscious is not easy to capture. So therefore, we shouldn't talk about it too much until we've thought very carefully about how we're going to measure its existence or not. And that's why you get Chalmers and David Goff and all these people saying, yeah, an electron is conscious. Well, a single electron isn't conscious. The electrons in my brain moving around now in a network are aware. I can imagine, I can remember the past. I'm in the present. I can imagine the future. These electrons help me do that. That is the process of consciousness. That's what and I can abstract stuff. So I can design stuff in my brain that doesn't exist in reality and then go build it. That's what makes humans really special.
Plus, if your brain is separated in two by severing the corpus callosum, you have two consciousnesses in the same head. And
sure. Well, that's the saying. All you're doing is you're taking your conscious network, cut it into two, and then I think you get to the point where actually conscious, like you say, it's a dimmer switch. Like as you keep cutting that network up and up and up and up and up and up and up, you are realizing that the capability of the conscious entity decreases dramatically. And it's a very interesting philosophical thing. It's also deeply interesting, I suppose, for most humans, because you wake up every day and you're you, and you're like, you don't want to die, and you get hungry, and you want to be socialized, and all this stuff, and all these biological requirements that are being yanked in your brain, hacking your consciousness. But so I wanted to get one thing. I was going to say here, maybe we're way off track, but I don't think so. So what Chalmers and Goff and you and a lot of other people are saying is, what we want to see in a universe that doesn't have information, doesn't make decisions. Events just happen. What I'm searching for is not the origin of life or abiogenesis. I'm actually looking for the origin of decision-making, believe it or not, because the origin of decision-making is really the origin of life.
Okay.
And what I mean by that, if I've got two billiard balls or snooker balls that interact, whatever, I can look at their trajectories and say, right, I can map that out. How complex does the system need to be, and how many layers where basically the outcome looks like the system has made a decision, and if the system was to run that again, it would come to a different outcome because it made a different decision. For me, I'm deeply troubled and deeply excited by this whole idea in almost equal measure, because I have no understanding of what that means in terms of origin of life and selection. But I think decision making is more primal than biology.
Do you have a theory and hypothesis as to the origin of decision making?
Yeah, so decision making actually, the origin of decision making is basically you have to have a memory. So that's
Right.
in pre-biology. So that memory allows you to store some information about the environment, and that you have competing memories, if you like. And if our entire drive, if the meaning of life is just to survive, which I suspect it is, then all decisions you make, whether you like it or not, you may make highfalutin decisions. Say, I may have bought this car because I like it and it's got the right engine and I want to be green. No, you bought the car because you want to survive. Everything you do is basically hacked by biology. In fact, your entire consciousness, your entire personality, everything is hacked by biology to do one thing, that is persist. And
So
you have
we are
lots of ways to do
competing
it.
wills, basically.
Yeah.
I can't remember which philosopher said that, but um, every single individual is a competing will for the same resources or overlapping resources. Okay, so I'm curious again. So you mentioned a little bit about your work, and you talked about your chemical computers, basically, that are basically selecting chemically. Could you explain how that works in a, well, I suppose my audience won't all be chemists. Very few of them probably will be, but in a sort of general sense.
Yeah, that's a good point. So because I'm interested in decision making and also how we can do computing, what I wanted to do is basically, in the same way that you would program a computer, I wanted to know, could I take a chemical system and turn it into like a microprocessor, where I can have I could do some processing, I can have some memory, and I could basically give it some information. The chemical computer would take that information, process it, and give me an answer.
Sorry to interrupt you, but is that a little bit like, because I heard a little while ago they produced a very small DNA computer where you could basically record information in the basis of DNA. Is it that sort of thing?
It's like that in a way, but what we've got here is with DNA computer, the DNA computers are kind of, they're all mostly memory and some rules where you can do what we call Turing complete, stuff, which means in principle you could turn your DNA computer and the computer to do anything. It would just be very, very slow because you've got to make and read the DNA. What we want to do is really make our chemical computer real time and almost to compete with quantum computing, or probably better to be complementary. And so what we're trying to do, if you can see the cube behind me, where you can see, maybe I'll bring it over, use it as a prop if I'm going to kill it.
It reminds me of Aurak from the old TV series Blake 7.
Yeah, it is. It's very, So if you see it in this cube, you've got a three-dimensional array, a lot of LEDs going on and off. The LEDs are all being addressed by a board underneath, so that board is programming it. If you can imagine that each of these LEDs was some chemicals in a test tube, and what we've done is we allow all the test tubes to talk to each other. Now, here the LEDs are being controlled centrally, but in our test tube computer, all the test tubes are talking to each other locally, like on a network, like peer-to-peer, like when like in a rock concert where you're all doing a Mexican wave or something like that. So if you can allow the chemistry, and a better way to look, it's almost think about like an ant, where ants talk to one another, work around. They've got a certain number of messengers they can give to each other, and then they can do quite complex phenomena. So what we're trying to do is make every chem bit talk to the other chem bit and do very simple operations. And if you can scale it over many chem bits,
right,
you have a very powerful computer for doing all sorts of very special kind of computations, minimizing energies, calculating stock prices, hiding information, solving kind of combinatorial problems.
Okay.
And that's what we're playing with, if we can instantiate that in this type of device. And also learn how computation can emerge in other manner. Lots of people have theories about whether, like Max Tegmark, I said, would say, is the universe a computer? Did it emerge? And is it a mathematical system that just is a computer? And one of the things I'm interested in is, did chemistry invent prime numbers? What is it about chemistry that gives you prime numbers? I mean, there's maybe that's a lunacy, you know, a silly question, but I don't think so.
Okay, okay. So these I'm just trying to get my head around it. I'm really curious about this machine. So you've got your chem bits, and you're monitoring information from them, and that's being turned into these lights that we can see, or at least in another lab it is. Um, First of all, do you have a selection pressure that you are putting onto these chem bits so that you can select the ones
Yes,
that?
each chem bit in this case has an input device to
Okay,
switch the bit on and off. And then
okay.
that chem bit can then interact with the next bit, and there's a device there switching it on and off. But because they can communicate with each other, there's another layer of information processing that
Ah,
occurs. So in the same way in your silicon trip, you have all these wires going in. Into our chemical computer, you have a whole bunch of inputs that go into these where you've got the LED, the equivalent of the LEDs. Remember, this is just a model. It's not really what.
yeah, yeah,
Uh,
yeah.
but in 3D, so there's like a wave that connects all the bits together. Now, I was inspired to make this because your brain is a chemical computer.
It is indeed. It is. So,
And it's the best chemical computer we know. It's the most complicated one in the universe. It has many trillions of possible configurations. And the reason we wanted to do this is the reason why you hated chemistry at school, the mole calculations. But if you thought about this, if we've got molecules in here in 18 milliliters of water, okay, so 18 is a molecular weight of water, you have an Avogadro's number of molecules. So that's, times 6 times 10 to the 22 molecules. So in in that 18 mil, you've got more molecules than you have microprocessors on planet Earth.
okay.
So if you could do information or processing in each molecule of water, in 18 mils of water, then you have more computing power literally in a cup than the planet does. And that for me is kind of like an interesting target to kind of get to kind of ask myself the question, well, how do I actually tap into that scale of computing, and what problems can I use it to solve?
I was just going to ask, how do you tap into it? So how are you monitoring these test tubes, and what are you monitoring within them?
So I mean, the current device we've got at the moment, we're using a web camera just to read out the states, but we use a much more sophisticated kind of what we call an ion camera, which just basically feels the saltiness of the surface of the device. And it's a bit like we're going to try to emulate the brain, right? The brain has very basic input and output. It has, your nervous system, your eyes, your ears, your touch, things like that. So we want to try and do something like that with our chemical system.
Okay, okay. And have you made much progress?
Yeah. I can't say too much at the moment, but yeah, there's a lot happening. We have got a universal chemical computer in the lab. So that means we have a universal programmable chemical computer. That all sounds very grand. Universal is important because that means it's like a Turing machine, which means it can run any program. It's programmable. That means it has memory and processing ability. And it's a chemical computer, so it does it all in chemistry.
And sorry, I don't want to, take too much information from you. I know you've probably got publications that are waiting, but are we talking about this computer performing and or and nor functions and that kind of thing, or is it different?
It can do that, but that's a bit below it. I think doing logic doing kind of digital logic on a chemical computer misses the point of what chemical computers can do better. To do digital logic, you need to wire together all the gates in a certain topology.
Right.
What you can do in a chemical computer is really emulate what happens in the brain and have emergence of networks of information. So we have to encode the information in a slightly different way, but this way allows us to so I would say approximately emulates what a quantum computer does, but it does it with chemistry at room temperature, with error correction that is much easier.
That's fascinating. That is really fascinating. So where would you see the future of this going? If your experiments are all successful, if the work goes in the direction you hope it will, do you see the equivalent of the Silicon Valley IT revolution, but with chemical computers? Or is that just a bit too grand?
No, I think actually the only way we're going to get to artificial general intelligence is using chemical computers. Why? What is the barrier to intelligence? The barrier to intelligence right now, well, is that you don't have enough states, so there's not enough resource in the microchip, and also the way the chips are trained to do machine learning and artificial intelligence is not. They don't have any understanding of the universe, no cognition, no common sense, no symbolic representations that give rise to an abstraction. So what I'm trying to do is invent a brain gel, and that brain gel is going to understand the universe.
Oh, wow.
And that brain gel is going to be the route we get to AGI. And you know, and that's pretty scary, but it's also pretty exciting, because there is no way we are going to get to anywhere approximating human intelligence with silicon. And there's just one reason. It's because it's not configurable. It's not plastic enough.
Okay.
In a silicon chip, you can put a maximum of 10 billion, well, about 10 billion transistors. In your brain, you have more possible configurations of your brain. That is, like, I don't know, 84 billion neurons, 10,000 connections per neuron. There are more possible configurations of your brain than there are particles in the universe.
I've always found that fascinating.
That is why you are you and I am me, and you know, we have the same processes in our computers that do exactly the same thing.
Mm-hmm. So rather than and or and nor and all of that kind of thing, obviously I'm a biologist, so I think in neurons anyway. You've got the equivalent of a neuron. You have several other neurons or the equivalent of those that are inputting information. Some are exciting that particular neuron, some are inhibiting, and depending on what the majority is, there is either an output from that neuron or it's inhibited. Is it that kind of thing?
Yeah. I mean, it's that kind of thing, and also you have to treat your brain, your chemical brain, like a child. So you have to train it in the right order to get common sense.
Okay.
And then that's where the general intelligence comes in, because it gets layered into the structure of the brain.
Wow, this is fascinating. Do you anticipate one day you're in the lab? I'm picturing your lab now like one of those castles from one of the old 1930s movies, you know, the Frankenstein kind of thing. And suddenly you get the right configuration and it attains some sort of consciousness.
I mean, undoubtedly we will make a chemical consciousness, because the only other consciousness we know of are chemical.
Yeah.
But it'll be gradual. It will be gradual, very gradual. And we're not suddenly going to wake up with a Terminator in the basement. You know, it's just not going to happen. What we are going to do is we're going to basically come up with more and more general problem-solving machines. And you know, once Google and DeepMind, finish their thing, they're going to understand intelligence. No, they're going to understand how to hack human decision-making. That's all they're doing, because they're not understanding intelligence. Maybe they might be equivalent. I've already argued that decision-making is just for our longevity. But so I think there is a really interesting extension there.
I mean, I gave a small lecture a few months ago about artificial intelligence, and didn't even cross my mind to talk about it being biological or chemical in nature. I gave a 1.5 hour lecture, and it was all about what kind of computer intelligence, what kind of software will be the first sentient, non-evolved organism. But it's quite fascinating that actually, in reality, the first real AI, I mean, general intelligence or super intelligent AI, may actually be nothing to do with silicon or even quantum computers, but something entirely different.
No, it's just, I think it's pretty easy to show on the back of an envelope why you're not going to get AGI with a quantum computer or a silicon computer anytime soon. And that's because of AGI, we don't know, again, intelligence is built by the universe to maximize persistence in the environment. So, I can't say very much more. I mean, we probably should spend some time, if you want, explaining how the Genesis engine might go there, right? Because it might all be, these are all parts of the same problem. I would say there are 4 problems I want to understand. The origin of life is the easier of the hard problems, I think. Then there is kind of like the emergence of intelligence, if you like, from the origin of life. And then there is like from the origin of life, there's emergence of selection and evolution, open-ended. Then there's the emergence of kind of intelligence, if you like. And then there's emergence of consciousness, and then on the top of that, the emergence of abstraction. So all those things are connected together. You know, the top machines in the universe are abstracting machines. That's what you and I do.
Right.
That is, I think, why we're so far away from the AGI, because the very same problem that is preventing the AGI is preventing us understanding the origin of life and building artificial life. And what we're doing at the moment is busy copying it. So what Google and DeepMind are doing is they're copying some facets of intelligence, but all they're doing is machine learning. They're doing regression on things, and it's worse, right? You probably get, I don't really like machine learning. It's just mathematics. I was doing machine learning many years ago. It's not intelligent. It's just basically brute forcing solutions to problems without any understanding. And I know Max Tegmark wants to use machine learning to get the laws of physics, but you could just go out and go, oh, that looks interesting. I'll make some measurements. Oh, I'll invent an inverse square law. Or you could come up with an AI that will give you a huge equation. And what I would say about the laws of the universe are maximally compressed representations, maximally compressed minimum forms to demonstrate that maximum notion of how the world is. We could make a machine learning algorithm that would teach you how to do mathematics and gravity, but it could be a massive black box, and you show someone that equation or that data set and the model, and they won't understand how gravity works. Whereas if you go to a child and say, look, two masses attract to each other, and then there's a force, and that is basically controlled by 1/r² of the distance between them, and also it's the product of the masses divided by r². And they go, oh yeah, cool, I now understand gravity. So the problem is that AI doesn't give you abstract understanding. It just gives you some.
Okay, I see. That's interesting. I understand what you're saying completely, and I'm inclined to agree. But I'm thinking back to the first major AI conference, I suppose it was. I think it was in Puerto Rico, put together by Elon Musk about 10 years ago. The first proper conference where they talked about the possibility of human level AI and the dangers and the existential risks and that kind of thing. And I remember that Elon Musk, Max Tegmark was involved in that as well. There was a vote at the end of a conference, and all the people there were, I suppose this might be part of the problem, all of the people there were computer scientists and engineers and those sorts of people. And they were asked, first of all, do you think that human level AI is possible? Yes or no? And then second, when do you think it will happen? And obviously there was a big stretch of belief. Some people said worrying about human level AI is like worrying about overpopulation on Mars. That was one person's quote, saying that it's so far away. But when you averaged everyone's votes out, they all pretty much agreed that human level AI would occur, and that it would probably occur within the next 20 to 25 years. I'm guessing you disagree with that.
Well, nonsense.
Yeah.
So I would like there to be a human level AI, but I'll tell you what, and it's not going to be in 25 years. It's not because I'm a naysayer. I'm like the craziest scientist you can find, right, in terms of doing chemistry and dreaming origin of life, things, looking for aliens. But there's a really important reason. The engineers, everyone looks at exponential problems and says, oh, it's just a numbers game. Well, again, if you look at the number of configurations of the brain and look at what you've got on planet, even if you connected every microprocessor to every other processor on Earth, you would get nothing approaching an AI, artificial general intelligence. Now, it's clear that you're going to get better and better chatbots and better robots and better self-driving cars, and they may look indistinguishable, but don't think for a second that they are generally intelligent. They are just really sophisticated AIs with lots of tricks. Now, my fear is that actually intelligence was invented by evolution over 4 billion years. And if you think about it, Luca then gives rise to then where you start getting, all these, the internalization of, you know, the mitochondria, you know, sorry, making these very complex biological cells, then plant, then animals, and so on. And then now we start to look at and cognate in our environment. We can interact in the environment and build models when we're primates, or even before as rodents. And then, so we have a spatial understanding. We know how it works in space. So that cognition and that interaction in the world allows us to start having a structure that allows us to kind of imagine where we are in space and time. That imagination of where we are in space and time and the need to solve problems in the environment and persist is invented by evolution. So let's go a bit further. All that selection from my cerebral cortex, my vision, the way I would see the world, and then we get to humans, ability to make tools and write things down, we invent language. And I think consciousness, if you like, or consciousness as we know now, was invented collectively and transmitted between humans by interacting. You bring up your child becomes conscious because you talk to it.
So do you think language is consciousness, but
well,
without language?
I don't know if language is needed for consciousness all the way around, but it's the way that you bring that in with cognition. But I'm saying if suddenly everybody got amnesia tonight, right, and they woke up tomorrow and couldn't speak, or maybe let's say everyone's memories got erased, they couldn't remember being a child, human race wouldn't be conscious. We'd have to invent it all again. Consciousness got invented by humans over time, culturally. Our cultural development, artistic development, all of that was developed over time. So for people like Elon Musk, just to say, oh, I'm worried about AGI, it's like, he just doesn't know what he's talking about. He's a good engineer. He's like Stephen Wolfram. He's a good mathematician and selling it. Like Craig Venter, good gene sequencer. He doesn't understand anything about the universe. Nothing. And that's why Elon Musk is like, he just talks, it's like, yeah, I'll talk bollocks for a day and you can give me some money because you're a billionaire, but look, there is no Terminator coming. And I'm both excited by that and sad about it at the same time. We need to understand.
To be honest, the chemical version of the Terminator that you're talking about would look more like the Blob, wouldn't it?
I don't know, maybe, but I mean, look, we might make a consciousness yet, right? If computer scientists can change the hardware, right, and make it more flexible, that's one way to get to AGI. So I might be wrong. If computer scientists could learn how to program that robot cognitively, that's another way of teaching it common sense and understanding the world. So that AGI. And it may be that we will invent artificial intelligence, general intelligence. It just won't be human. It will just be different.
Okay.
And that's kind of cool. And that will happen, but not now. And not on this trajectory. All we're going to do is have better chatbots and self-driving cars, and the future looks pretty bleak from that point of view. But luckily, we've got people in the UK who don't just live in a Silicon Valley bubble.
Well, it's fascinating. It's fascinating. I'm starting to become a little bit aware of the time now. Yeah, we've overrun slightly. So I'd just like to finish off by just sort of saying, is there anything we've not talked about that you would like to discuss for the last couple of minutes or so?
Yeah, I probably should tell you about the Genesis engine, because we talked about Abiogenesis and we went off on a big tangent and then we touched on it a bit. But it's all, the good news is we've already been talking about it. The chemical computer is a manifestation of the Abiogenesis engine. So what I'm building in my lab at the moment is I'm trying to do a couple of things. I'm trying to build a theory for biology and emergence of biology. And that theory is being constructed. I'm then also building a model that will then tell me how to make it. And then I'm building a machine, which we'll talk about, and I'm building a metric to measure it. Now, I'm very inspired by the way the Higgs boson was discovered, that we had a standard model. We then simulated that and worked out roughly where the energy is. We then built a particle accelerator, and then we went and looked for the Higgs, right? And that's what we need to do to build. And so I'm building an artificial Abiogenesis engine. That Biogenesis engine is based upon the theory of selection that goes beyond biology. And
Okay.
that model was telling us how long it's going to take to basically smash rocks together in a pot, basically, right? And then we've got a detector that allows us to detect when life is emerging. And that's really the exciting thing, that we've learned in the last few years how to find the emergence of living systems. And what we're doing right now in my lab is we've built a lot of robots that are mixing chemicals together randomly to start with, if you like, and letting those molecules interact with each other over time in different environments. And then we're seeing if the selection process emerges in that soup.
So you're not selecting yourself, you're letting it happen by, so you're not, so it's not like those computers where they teach an animal, a robot how to walk by selecting which ones are the best at it.
We're just waiting to see what happens. And
Okay.
all we're doing is we're looking for complexification. And that's it. And because complexification is a readout, a speedometer for memory.
Okay.
The more complex the object, the more memory was required to make it. And I've developed a new theory of complexity that explains that. So I'm trying to kind of, at the moment, kind of stress, because I'm trying to publish the new theory of complexity, trying to make the robot to use that complexity to show that it works, show that it's a general property of life. And everyone's like, it's like there's so many vectors going on, but it all converges around one thing. Build a robot has to build complex molecules. The complex molecules, when it makes them, is a readout of complexity, that there's some selection going on. The more complex the molecules, the more sophisticated the life form. And if we wait for long enough, we should have something that is, like what we've got now. How simple.
That's fascinating. That's fascinating. I can't wait to see those publications when they come out, to be honest.
We're trying to put more and more on the preprint server as well. And also what I'm doing later on this year is I've got a very good PhD student now, postdoc, and she's a really great artist. And we're working on a virtual art exhibit that we're going to show the group and just put all these concepts together in artwork and just show very pictorially what's going on, so people can come and interact, and it isn't just gobbledygook kind of computer science here. Because the problem is, you want to make this accessible, but the problem I have, because I think in physics and computer science and chemistry terms, these are very high level terms, and I'm probably one of the few people on the planet right now who happens to be an obsessive computer scientist, chemist, physicist and mathematician, whereas people are specialized in one of these things. And so breaking across those disciplines is really hard, even for the scientists.
Mm-hmm.
And we want to explain people, and it's not, I'm no genius. I'm just like a dude who likes to basically put mathematics into chemistry and program it with an Arduino. I mean, that's it, So I'm trying to then communicate that to people, to tell them how they should be excited, make it accessible, but really get deep into these questions. The origin of life, the origin of consciousness, is not a single discipline question. It's not just chemistry or biology. It's like an integration of a lot of things, and we'll need a lot of skills and a lot of willing people to come in and help us build that experiment over the next, 10, 20, 30 years, to understand if we can build life in the lab, we'll know for sure if we're alone in the universe or not, because we'll understand how hard or easy it is. Okay. And once we know that, we can then go and look at the exoplanets and see if we can detect the signatures of life. And I think by the time we get to the end of this century, if humanity makes it, in the next 80 years, we'll have detected life elsewhere outside our solar system. And that will be really exciting, because then the question will be like, well, if it's intelligent life, let's check, communicate with it, and maybe we should go and talk to it face to face, or whatever other life forms have. They may not have faces, they may have something else.
You see, there's a lot of science fiction people and scientists who basically say that, and again, I'm sure you'll disagree with this, that when we go out there, there won't be any organic or chemical life at all, because it will have all been superseded by some sort of electronic AI type life. I know you disagree with that, though.
No, I don't disagree with that. I think that the ultimate future of humanity is in some kind of hybrid AI, because evolution is occurring all the time. I'm just saying that it's not the solution to the problem right now, because it's too primitive. So I think that in the future, we will be making aeroplanes that fly themselves, but not with a silicon computer. We'll just grow a brain, and it'll be much less energy intensive. It'll be much better trained, and it'll be much more adaptive. It's a bit like but it might not be as controllable as a digital computer. So I just don't know. I mean, all I know is that selection has given me everything I have. Right. And if I break the causal chain between me and Luca, then there's something wrong. And I think that we have to understand that before we understand our position in the universe. And if life actually exists, or life is just a continuum of stuff going on from from matter with no memory to matter with open-ended memory. I did say to NASA once, the best way to go look for life is to just look for planets elsewhere where there's pornography. Look for alien porn. Then you'll be sure to find life elsewhere because the amount of pornography going on the internet was kind of annoying me at the time. A few years ago when the bandwidth was low, I was like, I can't download my scientific papers probably because everyone is just watching porn. Oh, that's a good idea. Let's go search the universe for porn or alien porn.
Well, you probably share your internet connection at the university with the halls of residence, so that probably explains that. Okay. So on that point, I better let you go. It's been a fascinating discussion, actually. I'm sure my audience are going to really enjoy this. For anyone that would like to know a bit more about you, where can they find you, so to speak?
Just go to croninlab.com, and that will connect to Glasgow University. And also, if people have got questions, I try to answer emails from people who, as long as they're not crazy questions like, I'm going to prove you relativity is wrong and time's going in reverse. So people have questions, I do try and answer them, and they just email me at my email address in Glasgow.
Are you on the social medias, or do you not really?
Yeah, if you look at Lee Cronin on Twitter, I even got a TikTok account, but I'm not really sure what to do with TikTok. Out of my cultural zone. I think I'm going to burn something to some jazzy music, but there's TikTok I think I'm going to consume, not contribute to. There's some brilliant chemistry on TikTok and computer science. It's like YouTube without the ads, but much shorter.
You could definitely have that cube in the background. That would work well in TikTok.
I have put the cube on TikTok, and I have put my laser cutter. And I might put my cloud chamber, but I need to think of some decent music to put to the cloud chamber once I've built it.
Brilliant, brilliant. Okay, well, thanks a lot for this discussion. It's been fascinating. And I wish you all the best in your research. I'm certainly going to keep my eyes open for your papers when they get published.
Nice to talk to you, Mark, and we'll do it again sometime.
Yeah, hopefully. I look forward to it. Bye for now.
Thanks.
Well, I think you'll all agree that was a fascinating discussion. Professor Cronin certainly is performing some engaging and groundbreaking work. I'm looking forward to reading some of those papers when they come out. Okay, so thank you for listening. That's all for now. Just before I go, I'd just like to say that if you would like to know a bit more about myself, Professor Cronin has already told you his Twitter handle, etc. But if you'd like to know a bit more about Dr. Mark Darcy, then you can follow me on Twitter. My Twitter handle is @MarkOfTheD, MarkOfthe, capital D. You can also drop me an email. You can do that via my website, scienceontheedge.com, scienceontheedge.com. And if you find these podcasts valuable and you'd like me to continue doing them, I don't advertise as of yet on my podcast. So I'm basically doing this as a kind of voluntary service. But I do enjoy putting together these podcasts. But if you'd like to support me, there is actually a donation button on my website. You simply go to scienceontheedge.com, click on the donate button, and you can give as little as say $3. It will all help keep me motivated, so to speak. Okay, so that's all for now. Have a great day, guys, and I look forward to speaking with you all again very soon. Goodbye.